So, welcome to everybody. It's a pleasure to start this last morning section of our workshop with Stefan Sur. We speak about on the existence of dual solutions in Lorentzian optimal transport. Thank you very much.
Thank you very much. Welcome everybody to this last day of the conference. And thank you to the organizers for this beautiful workshop. Yeah, it's always a pleasure being in Italy, especially Pisa. I'm always having a blast. Yeah. Okay, so Lorentzian optimal transportation. We heard already Rob McCann talk a bit about that yesterday. It already appeared a bit in Jan Brenier's talk. But let me just sort of get you in the mood after 4 days of optimal transportation with a bit of folklore. What I mean by folklore, I come from differential geometry, and their folklore is always Riemannian geometry. Imagine you have yourself a complete Riemannian manifold, and you look at a specific cost function, which is simply the distance. So the most classical case of optimal transport you can imagine. And then you know that for all Borel measures on this manifold N, let's say with compact support, I mean, I don't want to be too complicated today. This is a bit of an overview talk, so I don't want to get too many into many technical details. There exists an optimal coupling. Okay, this is fine. But since I'm talking about dual solutions, I want to say that there exists a function phi from this manifold N to the real numbers. Incidentally, for this case, it's real valued, such that the integral over phi d nu minus integral over phi d mu is exactly the minimal cost of those two measures. And this function is actually one Lipschitz. You know that, yeah? Let me put this. Okay. So plus phi is 1 Lipschitz. Okay. So this is a very nice result, very classical. Now you can ask yourself the question, and this is not my question, that actually goes back to Jan Brenier. What is in this entire story, which I don't know, maybe took 40 years to complete in this form, what about it in Lorentzian geometry? So question, what about Lorentzian geometry? And why is this relevant? Yeah, because you already heard it today. Maybe we'll repeat it. Lorentzian geometry is the language of general relativity. So this is a question in mathematical relativity. So whichever way you are motivated, even mathematically, you can say, okay, this is just another type of smooth geometry that appears. Or if you're more motivated by physics, then you ask yourself, well, this is classical physics, like Newtonian gravitation, if you want. And not this exactly, but you can formulate it like this. And this is relativity. So what we can do in Newtonian physics, we should be able to do in relativistic physics. So for me, what is so we have now a smooth manifold and some Lorentzian metric on there. Lorentzian. What is for me a Lorentzian metric? Just to fix it once and for all for people in the room. This is a smooth 0,2 tensor field on M. That means it's an every tangent space. It's a bilinear form. And I expect these bilinear forms to be symmetric, non-degenerate. And the index, just to save the sign, or to fix the sign convention, is always 1. So my time-like directions are always negative. So what's the picture you know from your course in special relativity? Is in every tangent space you have this cone structure. You have 2 cones, and since my sign convention is the way it is, these are exactly the those vectors of length negative below 0. Then these are called time-like. These are the relevant directions of particles. Yeah? Everything that you see except light Everything that has mass has to travel inside here, yeah? All those trajectories. Then you have the light cones, where the length is 0, and since this is an indefinite bilinear form, these vectors don't need to be 0, unlike in Riemannian geometry. These are the null or light-like vectors. These are directions of photons. Everything you sort of light coming into you comes on those, on the boundary of this. And this is space-like outside, where the length is positive. And as far as trajectory is concerned, this is irrelevant. Nothing is going there. Okay, and my standing assumption here for being able to do any relevant variational analysis or minimization is that this thing should be globally hyperbolic. So assume mg is globally hyperbolic. Well, you don't need to precisely know what that means. It just means sort of this thing exists. Or if you know, you know, and otherwise, imagine either you take Minkowski space, so where all of this already becomes relevant, what I'm talking about to you today, what I will tell you today, Minkowski, or spaces, if you want a bit more relativistic, general relativistic, you take products R times the Riemannian manifold, and your metric is something, some function alpha of t minus time to t plus h, where this is Riemannian on sigma, and alpha is some positive valued smooth function. Yeah. You could also do without the alpha, it's also okay. Then you have a static splitting, then it's basically some form of Riemannian geometry that you're looking at. And if you have these scaling factors here, this is what becomes relevant in cosmology when you sort of try to model the entire universe, you know, as something expanding or contracting. This is sort of an expansion contraction factor here. Okay, but those type of spacetimes are completely enough for the picture today. So just for people who know a bit more, what I mean, what I'm talking about, which sort of spacetimes. Okay, so then if we look at this picture here, for example, then I have my sigma. And now I need to times r. And I have my cones in every tension space. It's geometry, so the pictures are always a bit wrong, even though they're very important. And I want to define some sort of cost function or some sort of distance on this spacetime. So those kind of structures don't have metrics by themselves, but they have what's called a time separation. And for the time separations, I need to define what the length of a curve is. And since I told you that not all directions are relevant in my geometry, basically those are irrelevant, I need to restrict sort of the class of curves that I'm looking at. And I want to look at causal curves, or some curve to M. In this case, this is product. By the way, globally hyperbolic spacetimes always have this product structure. Yeah, that's why it's not such a big restriction. This thing is causal. Let's say if it is. No, not at the metric level. No. That becomes a bit more. Yeah, you know. So I say this is future pointing, or let's say just causal for today. If gamma is differentiable, because I want to make a statement about the tangent vectors. There are more general definitions if you want, but for this purpose is enough. Differential plus the dt of gamma dot is always positive, so my curves travel like this, intersect here the space, and they go upward. And the length in the metric, this is G here, by the way, is always non-positive. So basically the tangent vectors point inside those cones. They can be on the boundary and maybe change if they want, but for general, yeah. But they cannot leave the cones. That's the point. And this gives me a cost function called the CG maybe of 2 points by simply saying, well, those curves have a length. I can define, oh, that was maybe a bit squashed here. I can define, so yeah, maybe let's put it this way. Yeah. Cost function C of 2 points defined as, and now I'm making an alternative. So let's see. I want to take, and now this is the, I write infimum because, well, Rob yesterday talked about maximizing. I want to minimize here just in accordance to everybody in the room except those people who know Lorentzian geometry, which are not too many. So I take minus the length of those curves, this infimum over not any curve, but I take gamma causal in this sense, and from x to y. So this is not a very deep definition. This is basically what you would see in Lorentzian geometry. The infimum there is a minimum if G is complete. In our case, it's also minimum, but I don't want to talk about that too much. It's an infimum. This infimum is an infimum sometimes over the empty set. And I want to say, so infimum if there exists a causal curve, or let's put it, maybe let's put it this another way. Make this the definition. Then I make a weird assumption that the infimum over the empty set is infinity. Yeah? So basically, if I don't have any causal curves, I just set it into infinity. This is not so super surprising. You know, those kind of things happen. This is just to exclude really curves going outside of those counts. Okay, so, and now, maybe a bit of history on this problem for this formulation is the original question comes from Jan Brenier. I think it's 92. Did I spell it wrong? Yeah, okay. From 92, where he asked this question, tell me something for this sort of cost function for parallel hyperplanes or for transport between parallel hyperplanes in Minkowski. Transport between parallel space-like hyperplanes. Space-like here means the normal is time-like, space-like hyperplanes, which is basically just a sort of picture like this. Hyperplanes in Minkowski. And then I think it took a while for this problem to pick up until maybe the early 2000s when Rob McCann, who talked about such things yesterday, and French mathematicians Bertrand and Puel started studying this problem. And they proved a few results. But the problem always remained in this sort of Minkowski affine geometry realm category, I'd say. Yeah? So, yes, what I wanted to say, one thing to note. You might have noticed that here, when I told you the folklore story, I took the distance, not the distance squared. And this is the reason is precisely that in Lorentzian geometry, you also take the infimum of length. So it's also a distance. Yeah? It's not distance squared. This has an important reason that this, what I write here, is the relativistic energy of curves. Not in an analytic sense, but in a geometric sense. Or in a physics sense, in a GR sense. So in Riemannian geometry, for analytic reasons, you prefer the distance squared because it has an easier variational analysis. In Lorentzian geometry, you should not really do that. I know people do that. I'm looking at Nicola. It's completely fine. But it's a bit unnatural to do that from a physics point of view or from a geometric point of view. That's why I prefer at the end, when we sort of write the annals of this area, should be formulated in this world. Yeah. So it's an L1 transport theory with all its problems. Yeah. Hmm? Hmm? Yes. Hmm? No. It's yeah. No, L2 is absolutely not possible. Yeah, that makes no sense. Yeah. Not against. I'm just saying, geometrically, it's not very natural. Yeah. I mean, when I think back to my supervisor, who was a Romanian geometer, or is a Romanian geometer, he would also say for the energy of he was working in close geodesics, he would say that if you look at the energy, it's analytically the right tool, but geometrically, it's not the wrong concept. You should really talk only about lengths, not energies of curves, if you want the geometry. Yeah? Same thing here. Okay. So maybe a few facts that we get something started here. Fact one, we have existence of minimizers. Existence of minimizers for points or for pairs of points, pairs x, y, with the property that my cost function there, or the Lorentzian distance, time separation, whatever, is smaller than infinity. First of all, it's always bigger than minus infinity. This is already something that comes from this globally hyperbolic assumption. But that you then actually have convergence of curves is another step. Yeah? So it's what's called, ettore, what's it called? I forgot the name. What's the name of the existence of minimizers? Yeah, yeah, Aves-Seifert theorem. Thank you. So, and those minimizers, they are, what did I just say? Existence of minimizers, and they are pre-geodesics. So that means if you parameterize them with an affine parameter, their length with respect to my metric becomes constant. That means that they fall into two classes. Either their minimal length is negative, then their tangent vectors are always inside the cones of these minimizers, or the minimal length is 0, then they are always on the boundary of the cones. So there's only sort of these geodesics fall into two categories. In trajectories of massive particles when they're inside the cones, or photons when they're on the boundary of the cones. Nothing else. So they cannot change character. That simply, that relies on the fact that the metric square is a first integral of the geodesic flow. As you know this from your course in Romanian geometry. So, what did I? No, didn't want to go that high up. So let's see. So then I have another fact. If I write fact 1, I should write fact 2. If I have two Borel measures, probability measures on my space, let's say with compact support, then I get a minimal coupling. Yeah? Of course, in this generality, the minimal cost can be infinite. And then, of course, you have the question, the same sort of question that you formulate here. When is this infimum actually real or smaller than infinity? You can ask the same question here. Here, it's just basically the existence of such a curve. Here, you can write down a criterion. I don't want to talk about that today, but you can exactly say when such a thing exists, such a causal coupling, basically. Okay. Then maybe so. So with, and the sort of the oldest question in optimal transportation is so-called Monge problem. And you can already say that here. I can give you a solution to this. That if you, so let me see that I don't get the assumptions wrong. So we have two probability measures on my space such that their minimal cost between mu and nu, which is just the infimum over, you know this, CdP, Cg. In my case here, Cg, I'll just see d pi, where pi is a coupling of mu and nu. When this is finite and mu is absolutely continuous with respect to the Lebesgue measure of G. This is standard in pseudo-Riemannian geometry. You know this from Riemannian geometry. Same argument, you get a Lebesgue measure. Then the optimal coupling that exists is actually supported on a graph. So the unique optimal coupling is supported on a graph. So there's no ambiguity. Yeah? Jan yesterday talked about this early universe reconstruction problem. In his world, or when he formulated that 20 years ago, their solution was not fully relativistic. I think he mentioned that yesterday. They did that in a sort of semi-classical approximation. With this theorem here, you can actually do it in full generality in GR. Because what you do is, as Jan described yesterday, you start with something, some uniform distribution very early very close to the Big Bang. And a uniform distribution means you satisfy this. And then you have your evolution of your universe away from the Big Bang. And in GR, this is always drawn expanding because we expect our universe to expand. And then you have your observer here. Observer. And what does he see when he looks at the night sky? So when he looks at mass distribution in the universe on very large scales, he takes a picture of the night sky, which is simply looking at his causal past. To say basically those points which you can only reach by those light null geodesics. Yeah. Maybe I should. Do I have? Yeah, I have colored chalk. So let's see. So this is and I draw this like this because actually, you know this from science popularization, that the microwave background is actually sort of the earliest image we can take from something close to the Big Bang. And then you have a bunch of galaxy clusters here on your night sky. And then the question is, this is a certain mass distribution. You assume you have your uniform distribution in the back in the past, and then you ask, well, is there sort of, can I assign to each point a point here? Yes, and then this says sort of yes. You have trajectories here coming out of this, and it's part of this Seldovich assumption that there is no interaction between particles, that it makes it accessible to optimal transportation. Okay, what did I want to say next? Yeah. So, yeah. All right. So now, since I already drawn something dynamical there, I should tell you that in... Oh, I already erased that. For those metrics, I said it's sufficient to look at them. That's pretty obvious. In the full generality, it's not much harder if you know the right abstract theorems. That is fact 3. I get what's called a measurable selection. So there exists measurable selection as from those points where the this is the pair of points where actually my distance function is smaller than infinity, to the set of curves in the C0 topology. This is, let's say, 0, 1 to M, where every such that S, X, Y is a minimizer between X and Y. Yeah, so I can measurably select the minimal geodesic. Same thing as Riemannian geometry, you know this. Okay. And since this map is measurable, we get dynamical optimal couplings. Right? Yes. So now the fun starts, because then we can ask, what is actually the structure of those dynamical optimal couplings? You know, what their internal structure? Here I drew those curves nicely parallel, yeah, but this is a one-dimensional picture basically, so don't expect too much insight from low-dimensional pictures in geometry, if you're not doing low-dimensional geometry. But I can give you structure of dynamical optimal couplings. There's one important theorem, which is the so-called Mather. So for me, this is the Mather graph theorem. I think in this community it's called maybe Monge-Mather coding or whatever. But where I come from, this is the Mather graph theorem that says, let's see, if I take the canonical projection from the tangent bundle to the manifold, so basically every tangent vector knows its base point, and restrict this map, restricted to the tangents in an optimal coupling, in a dynamical optimal coupling, this map is injective. That just means those minimizers here, they cannot cross. I cannot have two curves, two minimizers in my support of my dynamical optimal coupling, which intersect. And moreover, it's actually better than this. And the left inverse is 1.5 Hölder. It is locally Lipschitz. Near time-like points, or time-like vectors, let's say, time-like points. Yeah, so if I know that I'm transporting in some directions inside the cone, I have the same result as in the Riemannian case, yeah, because in the Riemannian case, this map here is not missing, and this 1/2 Hölder is actually Lipschitz. Yeah. So the problem appears actually at those points which are light-like transported. And the statement is actually optimal. Optimal by example. Hmm? Oh yeah. You choose some complete Romanian background metric, and since this is a purely local statement, it's all the same. Yeah, doesn't depend on. Yeah, right. Yeah, you need some. It's true. And optimal by example in Minkowski. So simple geometries will not save you here. Just a set of measures is too big, yeah? A certain way. Okay, that was the first remark I wanted to make at this point. What is the sort of, there are probably many applications for this theorem in Riemannian geometry or in Riemannian optimal transportation, or let's say positive definite optimal transportation. And one of those applications is that if your initial measure is absolutely continuous with respect to the Lebesgue measure, then in the Riemannian case, you know that all intermediate measures up to the very last one, except that one, are also absolutely continuous with respect to Lebesgue. Yeah? So sort of optimal transportation cannot concentrate immediately. Yeah? That's what it says. And the same here is true if you assume this plus mu is concentrated on an achronal hypersurface for hypersurface, which, for example, applies to this example here of the early universe reconstruction problem, or if you want, just take one of those sigmas in my definition or my class of metrics I looked at. So basically, you have some blob of mu down here. You want to transport it to some nu that is concentrated here, and then you have a certain transport map, yeah, or whatever it does. And under those assumptions, you actually know that the mu t, the intermediate measures, are also absolutely continuous with respect to Lebesgue, as long as they actually can. Yeah? Even though you only have the Hölder. You save at least that fact. Okay, so now I have to. Okay, so now since I wanted to talk about dual solutions, according to my title, let me tell you a little bit about dual solutions, because this becomes then relevant. Okay, so what do it's already, I think, in every book on optimal transportation, that when you have such a cost function, finite valued or not, you can look at the dual problem. Basically asking so let's see, how did I formulate this? So we have Kantorovich duality. Duality. So we know that we have the minimal cost, transport cost between our measures in our spacetime. And this is exactly the supremum over the following set. You integrate some function phi over d nu minus phi d nu. And now we have to say a few things on phi. First of all, phi should be integrable with respect to those measures. This is not a big assumption, but I want that phi of y minus phi of x smaller or equal than my cost function. This is the usual assumption for writing down the Kantorovich duality. This is still true. I think this is probably, it's first of all not difficult to prove if you know the right statements. And second, I think this has been done before in a much more general context, but this applies here. And then if you have, this is a supremum, then you ask, is this a maximum? Do you actually have existence of this? Does this phi exist to make this thing equal? Because if you look at it under this condition, smaller equal, you actually have that this is always smaller equal than this, naturally. But equality is always the thing. So then we say, so phi solves the dual Kantorovich problem. If equality here in star, this is star. I want equality here in this. Maybe I should make the star here. Put the star here. So, all right. And the first remark you have to, why do I say something like this? solutions do not always exist. Solutions do not always exist. I think that was already realized by Rob McCann very early on, because if you just take Minkowski with, for example, R2 with dx squared minus dy squared as the metric, so everything is one-dimensional, and you take the one-dimensional, the back measure on the unit interval, on the horizontal line, 0, 1, transport that to height 1 to the interval exactly above, 1, 2, take the uniform distributions of those intervals, then the only chance to transport it is exactly along the diagonals. And this is a purely light-like transport. Yeah? So the transport minimal transport cost is here 0. And any dual solution would have to have infinite slope at every point. Because my cost function here has a Hölder, 1/2 Hölder behavior at the boundary, which also is responsible for this 1/2 Hölder here in the graph theorem. So, and a function that has infinite slope everywhere doesn't exist. So basically, when you start constructing such a function, you will see by this usual zigzagging around method, we'll see that this converges to minus infinity if you nail it fixed at one point. Okay, then maybe I'm running a bit out of time. So we have this problem that solutions do not always exist, but I can give you at least some hope. Existence for the under some conditions. So we have compact support. Okay, leave that. For the support of new connected and a time-like coupling. So what I assume, I have two measures, mu and nu. And what I assume is that I do get some sort of coupling where each point in the support of mu is only coupled to some point in some other points in nu, and those relation here is actually time-like. So it's negative. Yeah? This is x, this is y. This coupling doesn't need to be optimal. I just need some way of pushing mu to nu along particle paths. That's all I need. Then I get an existence of a dual solution under this connectedness assumption on the support. Okay. And the support of this optimal coupling is then, of course, contained in the subgradient of this dual solution, but this is not so super important at this point. So the remark here is not every dual solution is Lipschitz or locally Lipschitz. So the duals, you can have transports with dual solutions which transport something along the light cone. It's not completely excluded by this, but it should not be too much. That's the first one. Second one, generically, you can satisfy those assumptions. So every pair of measures you can approximate by measures in the weak stars topology, which have those two properties. Okay, so the non-existence is some sort of a sparse set of cases. Sparse, still very large. Yeah? Yes, causally related. Yeah. Yeah. Basically, what you do is you just push mu a bit into the future. The connectedness assumptions is because there is a connection argument in the proof. which basically when you do these constructions with the zigzags, when you construct the dual solutions, what you need to ensure is that the set you can reach is everything. And with the existence of this time-like coupling, I know that I can reach some open set. And then I make a connected argument saying, what I reach is open, what I cannot reach is also open. So it must be everything because I reach something. Yeah? No. It's just made it more complicated. Yeah. Maybe I should. Yeah. Okay. So, and the last, or maybe, yeah, the last theorem I will tell you, then I will stop. Maybe up to some, hold on, generic existence. So the last theorem is the converse question: what do I know about null or transports along light-like directions if I have a dual solution? So existence of a dual solution plus mu absolutely continuous with respect to Lebesgue. And disjoint support. So disjoint support. Maybe that's just to give you the precise sort of set of assumptions. Then the null transport, so basically the points which are transported along null geodesics, or along the boundary, is Lebesgue negligible. Lebesgue negligible. So basically, when I know that I have a dual solution, only very little can, in a measure theoretic sense, geometrically can still be a lot, can be hypersurfaces. It can be transported along null geodesics. Yeah? So sort of if you just look at it from a measure theoretic point of view, it's not such a big problem. Okay. So maybe last remark, maybe just verbally, since I mentioned my co-authors at the beginning. So that theorem sort of triggered me to ask, can I characterize this much better than just Lebesgue negligible? And in the 1 + 1 dimensional case, you can say something about, with the help of some weird dimension, box dimension notions. And the second remark I wanted to, this Alec Match from Cologne, he's a joint PhD student with Markus Kunze. He recently, just this week, he put it on the archive, wrote a long paper generalizing the results of Nicola and Figali on the rectifiability of the domain or of boundary of domains of these dual solutions. So, yeah, maybe I'm finished. One last sentence. Maybe if you're not just interested in things like this, there's an interesting point to this from the fluid dynamic point of view. These dual solutions, they come as gradients, yeah? And those gradients, they satisfy then an Euler equation. And this is the most simple Euler equation you can imagine. It's pressureless and static, since this is L1. Still, it seems that there are such simple solutions of the Euler equations which generate some sort of singular behavior. Singular behavior means if I look at the existence of this existence theorem, I know that even under those assumptions, there are points which are light-like transported, null transported. So physically what I see is I see two mass distributions in the universe, some, for example, dust and an evolution between them. And nonetheless, I do not get a bound on the internal speed of particles in there. Because that there is null transport means that some particles are sort of infinitely accelerated. The question is, well, do we see this in physical world? I don't know. And second, if not, what is the condition that we need to satisfy in order to exclude it? Because at this point, I have no really clue how to exclude this null transports. If you look back at this example, it's, for example, not in the regularity of the density. You could say, okay, if I have two densities, Lipschitz continues and so on and so forth, then this should not happen, this null transport. And the answer is no, because of this example. So it must be some combination of this time-like coupling plus maybe Lipschitzidity of the density could maybe do something like this. But I want to stop this because I'm already running over time. Yeah, thank you.
Thank you very much for this very nice talk. Are there questions? No?
Yeah, can I ask another one? Yes. Okay, so I know I understand that geometrically speaking maybe it's not relevant, but so I'm curious whether so that theorem about existence in the case what I mean if that adapts also to the case of where the cost is the time like separation square root or
yeah. This is you can do that.
So it works the same. So
it's
just
not written,
the existence of one.
Hold on, it's not written up.
I don't care. So if there existed one timeline coupling, regardless of then if there exists just one time like coupling,
then you should get a dual solution.
Oh, okay, very well. Thank you. Okay, thank you.
Does it make sense to study unbalanced optimal transport?
It absolutely makes sense, yes. Maybe that's another point to this last what I said. Maybe in the unbalanced case, if you only if you're free to choose what you transport, it might help you sort of push things away from the light cone. Because when you look at it just naively, you would say, why the hell would something go along the light cone? Yeah? Because it just makes things bigger. It's like going a detour where it's not necessary. But I don't know. That's actually probably a decent point to start a PhD.
Okay, if there are no other questions, let's thank Stefan again. And we have for a couple of minutes and we can start with the second talk.
Yes.
Okay, so we can continue with the talk of Dario Trevisan from Pisa on asymptotics for random quadratic transportation cost. Thank you.
Thanks, Giuseppe, and thanks to all of you for being here till the very end. So this is a joint work with Michael Goldman and Martin Husman. They're not here, unfortunately, this week, but I'm very excited to announce this result. So we deal with random quadratic transportation costs and their asymptotic behavior. But let me start from a completely discrete version, okay, which is related, of course, everything to optimal transport. You know maybe very well that from a combinatorial point of view, optimal transport can be thought as a special case of the assignment problem. So what is the assignment problem or bipartite matching? Is a problem where you have a set of objects, or rather two sets of objects, like workers and jobs, teachers, and the rooms where they should teach their lectures and so on. And you want to find an optimal correspondence between the two sets. And notice that they have the same number of elements. This is actually a special case because in general, you may also have more teachers than jobs and so on. So given two sets of these objects, for the moment, think of abstract objects, and you have a cost function for assigning, I don't know, worker xi to the job yj. So you look for a minimum average cost among all the possible permutations. Actually, this problem, this combinatorial discrete problem appeared also in Jan Brenier's talk 2 days ago. So essentially, it's a discrete version of optimal transport, and you are minimizing all the possible permutations, but you know that in specific cases, you can actually reduce a lot this complexity, okay? Now, and this is studied in many fields. Of course, there are efficient algorithms depending on the size of your problem, but it's not a NP hard problem. And it's studied in many fields. Actually, we borrow a lot of techniques from theoretical physics and statistics and probability, but there's also a lot of theory in algorithm and operational research. Now, what is the special case we're interested in? So we want to deal with the Euclidean and random setting. So let me tell you what I mean by Euclidean. Euclidean means that actually these points live in a Euclidean space and are D. So, and the cost is actually a function, a simple function of the Euclidean distance between them. So instead of a general cost, we move to a special case. Actually, also the function, we take a very simple function, okay? Just the power p of the Euclidean distance between point x and destination y. Of course, now, if the cost is this one, you may argue why p. So there was a question before in the Lorentzian case, right? Why should we add this exponent p to the length if instead just p equals 1 maybe is the most important thing? Well, you may think for modeling purposes that this is not the actual cost, but it's like a proxy for a more complicated cost. And this is used also in applied literature. Okay, so perhaps you see that you feel better that p, for example, a concave case, which would be p smaller than 1, is more realistic than the convex case, p larger than 1. So anyway, this is just half of the setting. The other point is that we're interested in the random problem. What I mean by random, the point is that these workers and jobs are actually random variables. So for each realization of this situation, where you have n points xi and other n points yj, these are randomly sampled, and then for each instant you solve the problem. So, and then the solution, the cost in particular, will be a random variable. But also the permutation which solves will be a random variable itself, okay? So this is still realistic because in many cases, you may say, okay, I don't really want to solve, for example, the worst case, the most general or bad situation that may appear, but I have a sort of generic situation, and my observation tell me that, for example, I can think of the workers are living random people in a city, and the jobs as well, also random people, random locations in a city. Okay, so bear in mind that this is quite different than the worst case analysis. So essentially, you may exploit randomness to say that you're far from the bad situations, okay? But also this opens the way to apply probabilistic techniques. So let me show you some simulations, and these are just 200 pairs of points randomly sampled on the unit square. And these are just, you see, red points are the workers, and the jobs are the blue points. And then you just need to assign, for example, in this case, we minimize, actually, all the simulations, we minimize the distance squared. Perhaps I should have changed a bit to show you what happens if you change the exponent. And you see, you have a lot of, these connections, of course, and typically they don't need to travel very far, okay? Actually, you can run similar situations in 3D, and this is why I prepared the slides in this way, because we can explore this cloud of points. This is very similar to Jan's slides, right, where he solved this early universe or matching problem. But instead, in this case, we have, say, two clouds of points, and then you just solve again with the squared cost, and you see a similar thing which happens. Of course, the connections, okay, it's more intricate, but typically the distances are not very long, okay? And this helps us to understand the question that we want to solve. Essentially, the first question is, okay, what would be the typical cost of this matching problem, this random assignment problem? What size will it be? Is there convergence when the number of points becomes very large? And actually, then we want to study fine asymptotics, typically for the structures of the solutions. So, but in this talk, we'll never actually discuss about the structure of these solutions, so the actual matchings, but we just focus on the costs, okay? So the first thing, which is very known and simple, is heuristics, so that if you have a cloud of n points in a cube, like the previous pictures, say that you are in dimension d, the typical distances between these points will be of order, so you imagine of a grid, so will be n to the minus 1 over d, because you have sort of to fill uniformly this cube. So if the typical distances between red and blue points will be like this, so the matching will be at this distance, the cost will be raised to the power p, and the summation will give you another n. So this should be the typical size of this random variable. Of course, there will be oscillations, but we expect this kind of behavior. And it is well known since I think 40 years that this is true for d larger or equal than 3, but becomes false in low dimensions. So essentially, this is why I showed you also a 3-dimensional simulations. But I'm not sure that you can see from just from one example that something changes between dimension 2 and 3. Okay, but if you run some statistics and you do some histograms of the lengths, you see that there is a distance also from small n's. And what is exact asymptotics? So if you look for run upper and lower bounds, there's this well-known result by Aitai, Komlos, and Tusnadi. And then Talagrand and Barth, Bordenave, and Ledoux improved on this. So essentially, we know that for any p, say, larger or equal than 1, you take two sets of independent uniform points on the cube. The expected value of this cost will be this rate. Let's call it RDPN, which you see is, okay, what you expect, the heuristics is correct for d larger or equal than 3, but then you have these corrections. For d equals 2, you have an extra log. And for d equals 1, there's even, you see the exponent here should be 1, instead you get 2. Okay, so it's way larger than what should be. And also in the concave case, it is known, okay, but I don't show you what happens, okay. So it's a similar situation. There are some corrections in low dimensions. Now, actually in dimension 1. The next question, so if you know how these random variables behave, and if you forget about, for example, the next question for a probabilist will be, okay, what can I say about the variance of these random variables? But let's forget about the variance and let's just look at the means. So the point is that we know the rate. So the question is now, can we say that actually when n becomes large, this expectation is not only of this rate in the sense that we have an upper and lower bound in terms of this function, but actually if you divide, if you renormalize, you have a limit, okay, which is pretty much expected because you have a sort of a very uniform situation. And actually, about limit results, the situation is instead a bit open, at least in some cases. So if you wonder about the limit of this quotient, when the number of points becomes larger, but still uniform on the cube, so it is known to exist, this limit, and to be strictly positive and finite, in all the cases, in all the cases, in dimension 1, almost all the cases. Actually, in dimension 1, there's only one concave case, which is p equal 1/2. In all the other cases, we know that the limit exists. In dimension 2, we know that the limit exists when p equals 2, and it's actually an open problem in all the cases, well, actually also p between 1 and 2. Sorry, let me correct. So d equals 2, we have actually, it is known if p is between 0 and 1 or d equals 2. Okay, so in the concave case, it is known to exist. Yes, or p equals 2, yes. So there's an entire window, say p larger or equal than 1, we don't know, except for p equals 2, where we can actually compute. And then in dimension 3, everything is known. Essentially, the limit exists. So for every p strictly positive, we know that we have this limit. And this is a collection of results, and I would say pretty much almost completes the picture. So if you want to put some effort, perhaps p equals 1, and dimension 2 is listed as an open problem by Talagrand. So if you want to make some progress and say that you solved the problem proposed by Talagrand. But now this is the picture. Of course, now you say, okay, but in practical applications of this, if you think of cities and workers and so on, or galaxies, as Brenier showed, actually, okay, you may think of uniform distributions, but you may think also of non-uniform distributions. And you would like to understand what happens if the points xi and yi are not uniformly distributed on the cube. They have some density. And of course, we take all of them with the same distribution, because it's a different problem if the points have different distributions as well. So, is it okay? Yeah. So the heuristics might be just slightly different. The point is, if you fix x in your space and you have a density lambda of x, and you look at a small cube, because still you expect the matching to be local, so of length r, you will see, depending on the density, you will have n times lambda of x r to the d points. Say that if the density is very smooth, you can approximate like this. And now you just simply need to understand that if these points are still on a grid, the typical distance will be n times lambda of x to the minus 1 over d, and then you do the same argument, and then you sum over all the possible locations, so you integrate with respect to this x, and you expect now this correction here. depending on your density. And you see also there's a problem here. If P becomes too large, now this becomes a negative power. So at least this heuristics works, say if the density is always strictly positive, okay? But let's forget about this point where the density can be negative and so on. So let's give you a theorem about this, which is again is a collection of results, which tells you that if D is larger or equal than 3, so let's forget about also the low dimensions because it's a different story. And P is, well, larger or equal than 1, but actually this works also for P strictly positive. You know that you can show that there are two constants. Let's call them alpha low, which depend on P and D, and alpha up, strictly positive and finite. So that for every, say, smooth and strictly positive density that you may take on your cube, if you sample these points now with this common distribution lambda and independently, well, you have two inequalities. One for the Leminf. So the Leminf of the cost renormalized by the rate will be larger than this constant times this integral of the density to the power, to the right power given by the heuristics. And also the lim sup will be bounded from above by this alpha upper times the same integral of the power. And now you may also ask what are these constants. Actually, we have a characterization of these constants, and these are given as follows. So the upper bound, you can show that coincides actually with the limit of the expected matching cost when the points are uniform on the cube. And the lower bound, it's again a limit for the expected matching where you do a different cost. Okay, there is this so-called boundary cost. And it is possible to show that these limits exist and when the points are uniform on the cube. And what is this boundary cost? Well, actually, this boundary cost is a modification of your original cost. So if you have a domain, instead of saying, okay, the worker can move to the job here, well, he can either move or if you want, you can move outside. If this is a country, can go outside, go abroad, and maybe there will be another worker coming and replacing his job. Okay, so it's a sort of import-export cost, and the only cost that you pay is if you want the distance from X to the boundary, and then from coming to the boundary to fill the job. Okay, so it's really a so-called boundary cost or import-export cost. And you see that this is slightly smaller because you allow for people to have two choices. Either you go and work in your country or you go abroad and then somebody else will come and replace your job. Okay, and so this is always smaller. This is the lower bound, and the upper bound instead is the classical matching with the Euclidean cost. Okay, and now it's a completely open problem, as far as I know, to show that in any case of D greater or equal than 3, okay, and any P positive, pick your favorite P to show that these two constants are the same, okay, and it is still an open problem, a bit embarrassing because somehow we can say a lot in special situations, but this is a quite natural conjecture to make, and so far there's, okay, what we have is a partial progress in this direction, but for a small variant of this problem. Now, just show me, just to show you some simulation here of the boundary cost. So you see, in dimension 2, you have the standard optimal matching assignment, as before. Now, if you allow for the boundary, you see these points close to the boundary that go away, and somebody else will come and do another job here, okay? Now, if you just make a small movie from the two, you see there is some change close to the boundary, but also some change inside. So it's not completely trivial what happens, right? And similar thing can be done in 3 dimensions. You see, this is just a classical transport, and then you see all these points that go to the boundary and others that come. Okay. Now, from a combinatorial point of view, you can say something, but it's not completely clear how to show just using combinatorics, if you want, or geometrical arguments. At least we tried a lot, but we were not able to make progress on this side. On the other side, it's quite nice that we can connect this problem to optimal transport, and using optimal transport tool, we can make some progress. And the connection is quite natural, and we are at the last day of the conference, so I'm just skipping a lot. So you know that this optimal assignment, if you relax, instead of looking at permutations, you go to general B-stochastic matrices, becomes, thanks to Birkhoff-Neumann theorem, gives you the same cost. And then you recognize that this is an instance of the Wasserstein cost of order P. Between what? Between the marginal or the empirical distributions. So instead of looking at the points, you do the measure, you do the empirical sum over delta measures at the xi. Okay. Actually, you see, here I prefer not necessarily to normalize mu and nu to be probabilities, okay? This will be also useful a bit later, okay? But anyway, as long as mu and nu have the same mass, you can do the Wasserstein cost of any order P, okay? I hope this is clear. And now, what is the good variant that we study? Essentially, instead of taking two clouds of points, with distribution lambda, you can do this semi-discrete transport. So you look at one cloud of point, you normalize so that this is also a probability distribution, and you do the empirical measure for that and the target measure. This is what we call also the matching to the reference measure. Okay, this is slightly more regular than just having the two cloud of points. Okay, and now what happens? Okay, from a say broad perspective, you may expect everything will be the same. So actually, it's slightly simpler to show this kind of results rather than for the two clouds of points. So for example, we can prove that for any dimension larger or equal than 3 and any P, actually P is strictly positive, we have these new constants, C low and C up, which replace this alpha low and alpha up. We don't know if they are the same or if they are related somehow. So that for any smooth and strictly positive density on the cube, you have formally the same kind of results because you have formally the same kind of heuristics. Okay, so you have the lim-inf and the lim-sup, where you replace the matching cost now with this Wasserstein distance, Wasserstein cost to the power P. Okay, and now again, what are these constants? Well, these constants are exactly as before, but you need to replace the matching with the Wasserstein cost. For the lower bound, this is interesting because there appears now an optimal transfer problem with this boundary cost as before. And again, you just need to replace with the correct definitions. Now, what I want to highlight is that the case P equal 2 was first introduced of this boundary cost, where essentially, again, you are free to transport mass to the boundary and import mass from the boundary, was first introduced by Gigli and Figalli, as far as I know, in the context of diffusions with Dirichlet boundary conditions, right? And then, of course, there was some progress on that. But it's quite natural from the point of view of these combinatorial optimization problems. Okay, so what is our result? So for every dimension d larger or equal than 3, we can actually show that for the quadratic cost, so for p equals 2, the c lower and c upper coincide. Okay, so this is essentially, I think, the first kind of result of this type, because previously it was known in very special situations. So for d equal 1 and the concave cost, smaller than 1/2 actually. So, but this is very, very special because you are on the line and you have a very specific structure of the costs. And then the other case was P equal D equal 2, where we can actually compute the analogs of this and we can show that they are the same. Okay, it's not a very nice proof because you compute these are 1 over 2 pi equals 1 over 2 pi. So you really have a proof that works in both cases and you show, okay, they're the same. So now, in this case, instead, we cannot compute who these constants are, but we show they are the same, which is something it's interesting. So what do we use in our proof? Just a small, maybe, I don't know, yes, a small slide highlighting the tools that we use. Okay, I will not give you the full proof, but just a bit of, say, ideas. So we use, crucially, a PDE ansatz both for the Wasserstein distance and this boundary Wasserstein. And then we exploit a lot of new results on the stability for optimal transport potentials. Okay, so essentially what we use is a quadratic response for the Kantorovich potentials. This is a result by Delalande and Merigot. And And then we employ these kind of results using some ideas from stochastic homogenization. In particular, we use what they call an intermediate scale Poincare inequality. Now, just to make a bit clear what we mean by this. So there's been a lot of progress in these matching, random matching problems, starting from an ansatz, an heuristics by Caracciolo, Parisi, Lucibello, and Sicuro in the statistical physics community, which they say simply, okay, if you have two measures on a domain, actually they work on the torus, well, replace the Wasserstein distance cost of order 2 just with a negative Sobolev energy. So what do I mean? I mean just you solve the PD, the elliptic PD Laplacian of f equal the difference of the two measures. And if you have a boundary, you should put the Neumann, null Neumann boundary conditions to ensure that you don't have flow exiting your boundary. And then you just replace the cost with the energy. Now, this is a very nice ansatz and gives you a lot of predictions. Some of them are very open, I would say, in particular in dimension larger or equal than 3. And we actually work using these kind of ideas. So we give you a lot of argument based on these ansatz, even if it's not very precise in dimension d equals 3 and larger. But if you... Exactly. No, for them it's really whatever densities are. So they apply it directly to the cloud of points. Now, yeah, okay, exactly. Exactly. So you can make this precise. So the first level, you can make this precise as an inequality based on the Coronia-Moser and Benamou-Brenier. And you know, if one of the two densities is bounded from below by some constant, then you get an upper bound, okay? You get an upper bound, and f is still the solution. F will always be the solution to the Neumann PD problem, okay? Now, but if you want to really turn this into an equality for d equals 2, you can do it. And this is what we did with Luigi and Federico Stra years ago. Now, for d larger or equal than 3, it's more tricky. And we expect this to be false. Essentially, if you look at very small scales, this ansatz phase. And Caracciolo and the others actually did a sort of non-rigorous renormalization to give away some divergences. So they say at very small scales, this phase, even the physicists say this. So we don't know if it's true or not, but we cannot prove it. While for larger scales, it should be still true. So this is, anyway, take this as really a formal approximation, okay? Now, you may ask, okay, what should I do now if I have the boundary cost? If you have the boundary cost, if you apply the same argument, the same ideas, you look at the potentials and so on, you understand that you need to put a different boundary conditions. You need to play with the null Dirichlet boundary conditions at the boundary. And now from this, yeah, okay, you can make this also rigorous if you want, but this will not be sufficient for us, essentially. Now, what you can also do is, okay, I know that optimal transport has a dual formulation, and what if I work with the dual formulations as well for these energies, okay? These are very standard things and are rigorous, okay? They're in green, okay? So if you want to explain, so write this energy in a dual formulation, you minimize over the vector fields, their L2, so their integral of the vector field squared with a constraint on the divergence, and if you are doing the Neumann boundary conditions, zero flux at the boundary. Well, for the Dirichlet case, you don't care about the flux at the boundary. Now, these dual formulations, which actually are closer to the primal formulation of optimal transport, gives you trivially that the Dirichlet energy is always smaller than the Neumann energy. So what we do is actually to show a converse inequality. And how do we work? Well, we start from the gradient of the Dirichlet solution. So you start from a vector field which is grad u, which may exit your boundary. So you have some flux at the boundary, and we just say, okay, we introduce a cutoff and try to correct for the error terms that will appear. So if you introduce a cutoff which is 1 at the boundary and 0 well inside, you may first do a correction of this kind. But of course, you destroy the divergence. And then, okay, and this is quite natural. So, and you may say, okay, maybe I should need some further corrections. So what is this divergence? You have a term, which is what happens inside your cutoff. Eta is 1, so close to the boundary. And then you have this sort of flux due to your cutoff. And you may introduce further corrections. In our case, it's quite crucial, this, if you want, key identity, which helps us to remove a dependence on grad u. Okay, so you see this divergence, you would like to be zero, this difference. Okay, we can correct it in many ways, but one crucial thing for us is to play with this integration, so this key identity, if you want. Why? Because it allows us to remove, you see, there's no more grad u here. And this is why essentially everything boils down to this, why we cannot do it for any p, because this works only for the p equal 2 case. Now, if you want to understand a bit better, we can discuss, but this is essentially our obstacle to extend to any p. Now, if you see this identity, you see, well, another correction should be u grad eta. So let me add this. And then if you want to add the other corrections, you just solve another PDE with what is left with null Neumann conditions, okay? So essentially, it's a very simple idea. You just want to bound the Dirichlet, sorry, the Neumann energy with the Dirichlet one. You start from the Dirichlet and you correct for the boundary conditions. Now, after this series of corrections, you know that this vector field will have an energy which is larger than the Neumann one because it has the right divergence and the right boundary condition, so zero flux at the boundary. And if you play a bit with the standard estimates for PDEs, you end up with this upper bound. So we have an upper bound of, this is just simple a PD result, okay? You can bound from above the energy of the Neumann minus the energy of the Dirichlet. Okay, there's a small epsilon you can play with. So it's still a small contribution for the Dirichlet energy, and then you have this term, which should be a reminder, so it should be something small. Now, this is just a result for a PDE, but we can turn this with some extra assumptions to a result for the Wasserstein distance. Okay, this slide is just to show off that we can do something for the actual Wasserstein distance. So this is, if you want an upper bound for the usual Wasserstein in terms of the boundary Wasserstein, which uses a cutoff, and okay, there are some error terms that possibly they should be small. Okay, so please, I don't want to enter into details, but you can really track the terms from the PD approximation into this plus some other error terms, okay, which appear only because you are dealing with the actual transport. Now, if you go back, now we have a good result, and we would like to apply it to our random setting, random assignment. Now, on a technical side, what we do is actually, instead of working on a single cube with a lot of points inside, we zoom in. So we work on a large cube of side length L, which is n to the 1 over d. Now, why this? Because then we know that the typical distances of this transport is now 1. So the heuristics is the transport is of order 1. Okay. And now, if you want to be rigorous, you need to use also Poisson point process, but let me skip on this. So our two limits, the C low and the C, oh, sorry, this is the C low and this is the C up, become these two limits. Okay, it's simply just a rescaling. Now, this is useful because now you can, at least to me, we can track a bit better the dependencies of the things. So do I have 10 minutes or 5 minutes or no? Yeah. Okay, good. Okay. So maybe I have time to give you also the other ingredients of our proof, maybe. So if you go back to the PDE ansatz, so let's forget again the optimal transport, because I think also in the PDE case, it's a sort of new result, but much simpler, okay? So if you go back to the PDE ansatz, what is the typical size, so the average on the cube of this gradient of u? So this replaces our average displacement. And this is, so from the PDE ansatz should be this, and we know it is of order 1, okay? So what information we have? We have that this cost is of order 1. Okay, roughly, let me emphasize, it's in average with respect to the randomness and in average with respect to the place, so the position. But roughly, let's say that the gradient of u is of order 1. And now, if you plug again our PDE inequality from the Neumann to Dirichlet upper bound, and you remember that you are scaling everything, so the cutoff should be of order delta L, so it's still of size of the length of your cube by a small factor delta, okay? And then eventually we will let first delta to 0 and then epsilon to 0 if you want. So you average everything with respect to the probability, you have this nice inequality, because this is this converges to the C up, this converges to C low, and if you let epsilon to 0, this disappears, and you hope that this term is of lower order. So you just need to show that these are error terms and are of lower order. And these are due to your cutoff, essentially. Now, let's focus a bit more on these terms. So we have two terms. One, if you remember, is due to the divergence that we have inside our region that is close to the boundary. And this is this term here. And the other term was the one due to the flux, which then eventually disappears a bit due to this integration by parts, so depends only on u squared and not on the gradient of u. Okay, even if in principle this flux had grad eta grad u. Thanks to the integration by parts, it depends only on u. But now you see that, okay, there's a bit of competition because here you see a delta to the minus 4, and you expect the delta to be taken small, so this will explode. But on the other side, this is good when delta is small, because delta is the size of your cutoff relative to the length of your cube. And you can expect, actually, you can prove that this becomes small. The first contribution is small if delta is small, because you want to do a small cutoff at the boundary. On the other side, this explodes. Why? Well, trivially, it explodes because the gradient of u is of order 1. You are on a cube of side length L, so you expect u to be of order L. Because if you have a function of gradient 1, the side, we can say at worst it should be of order L. By Poincare inequality, you can bound this with the L squared times the gradient, which this cancels exactly this L squared. So essentially, you say, well, this is actually exploding. So there is no way we can balance between the two. But then, okay, is this really true or not? I mean, we know that the gradient is of order 1, but perhaps these are random points, so there should be some oscillations. So the idea here is to show that actually this term, which trivially is of order L squared, thanks to oscillations, is actually smaller. Okay, this is an idea that comes from stochastic homogenization. Okay, you have these things that oscillate. If you just plug Poincare, you fail to capture the right case. So roughly what we want to show is the potentials, these solutions to the PDE are much smaller than what you would have trivially. And the idea is really to exploit cancellations. How do we exploit cancellations? Well, we introduce what is called an intermediate scale, a mesoscale, and we argue by comparison with a competitor built on the mesoscales. Okay. So what do we do more precisely? We take our huge cube, we partition it into these intermediate cubes. So you have L, and then you have L0, okay? So we do this partition, which is still becoming very large. In the limit, it's not like a scale 1. So L0 is also going to infinity. And then on each subcube, we solve the PDE, if you want to solve the PDE, or the optimal transport problem with boundary conditions with this boundary transport problem. So we solve on each subcube the PDE. And now, if you think of the PDE is much simpler, because you know that you have 0 boundary conditions on each subcube. So we glue together all these functions, thanks to the boundary conditions. And we build a global competitor. Let's call it U tilde, okay, which is built by gluing together the solutions on each subcube. Now, on each subcube, you have essentially these random points, and these are independent. At least they have the same distribution on each subcube. And we solve on each subcube a separate problem. So now, if you average the energy of this competitor built on each subcube, you have the same law on each subcube. So on average, you will get the same contribution, which is the solution on a single of these cubes. Okay, let's take the simplest cube, 0 as 0 to the power d. Okay, this is due to the so-called stationarity of this situation. So in law, they are the same. They're not exactly the same points. It's not really periodic, but in law, they have the same statistics. Okay, if you look at these different cubes. And now, since also L0 goes to infinity, you know that when L0 goes to infinity, you converge to C low, our limit, that this is known to exist. What does it mean? It means that even if U tilde is a competitor, when L0 becomes very large, you will have essentially the same energy as the optimizer, okay? So what does it mean? It means that you have this sort of the difference between the two, the actual solution U on the big cube and this competitor will be infinitesimal. And now, what you have, at least for the level of PDs, is that if you have a competitor whose energy is close to the actual optimizer, then the solution must be close to the optimizer, okay? So this is so-called stability of solutions is due to the uniform convexity of this energy. At the level of PD is very simple. And so you can cook up this inequality here. So you can show that U tilde is roughly, let's say, is much closer than, so it's very close to U. So the difference is infinitesimal with respect to L. And now what we also know is that U tilde is built by gluing together, patching together these solutions on these smaller cubes. So trivially, if you want by Poincaré, now on each subcube, you know that the gradient here will be of order 1, so U tilde on these subcubes will be of order L0. So now by triangle inequality, you gain that also this one will be of order L. We don't actually know the order. We know that will be infinitesimal with respect to L squared. Okay, because you have a contribution of this, which is qualitatively small, and this is quantitatively small. Okay, actually, it's a problem to make this complete argument quantitative. Okay, there's a lot of quantitative stochastic homogenization, but we are very, very far from their kind of results. Okay, in this setting. Now, you may wonder what happens to optimal transport. Optimal transport is not actually the PD. You're not actually solving this quadratic PD or any kind of uniformly convex energy, right? So actually, optimal transport is much closer to a linear programming problem, right? So what kind of stability would you expect? Actually, this is actually the technical point that spark all the result is this kind of results on stability of optimal transport. So Merigot maybe discussed a bit this kind of results. What we do is exploit a small variant, which is not for the quadratic cost, but for this boundary cost. And then they realized that it's possible to cook up more variants of this also for costs, which are just the P cost and so on, the power P. So essentially what you can show is that if you take a measure mu and you, for example, you take the Kantorovich potentials between mu and the Lebesgue, the uniform measure on your cube, say with a zero average, just to remove this. Then if you take any other competitor, so you take a pair of conjugate functions, and let's say that also the average of U tilde is 0, you have really what you want. So you have a sort of quadratic response in terms of stochastic homogenization. So you know that the distance, the L2 distance between the U's, U and U tilde, will be bounded by some constant, which depends on nothing in our setting, is a universal constant. Well, it depends on the dimension if you want. L squared, and then you have the distance between the actual cost, so the minimizer, and the competitor cost, if you want, which is in the dual formulation. Okay, so this is actually a non-trivial ingredient, but the proof is the one due by Delalande and Merigot, essentially. What we were able to do is to extend this also to general P, strictly larger than 1. So I suspect, we hope someday to be able to extend this kind of argument to non-quadratic cases, so P strictly larger than 1. Actually, P equals 1 may be a bit of a problem here, because we don't have, also in the PD case, you have some troubles. And also another possible extension, which would be very interesting, is to use this optimal transport argument to deal with the actual bipartite problem, so the original matching problem, this alpha low and alpha up. And finally, just to list another open problem is to obtain some rates of convergence for this kind of results, because the physicists really, I mean, using this approximation and very, say, non-rigorous renormalization tricks, they call it this way, they have some serious conjectures about the rates of convergence, which we are very far. We don't even have a quantitative rate so far. We know that these limits exist, but we don't have a quantitative rate, not even the one conjectured by the physicist. Okay, so with this I conclude, and thanks. Thank you. Thanks.
Thank you, Dario. Are there questions?
Thanks, Dario. I wanted to ask two quick questions. The first one is whether you run any simulations to check also for other values of P if the constants are equal.
No, actually, no, I'm not very good with simulations, but this could be a good project. But I suspect also we run some simulations in dimension 2 with different p's, and actually these limits seem to exist because in the papers by the physicists there were no simulations for p different than 2. And yes, you see really a convergence if you renormalize with the right power. So I would suspect it's safe to conjecture that all these limits exist and are the same, except for dimension 1 and p larger than 1/2. In this case, in that case, I suspect the limits should be different, the lower and upper. But it's a different story. Dimension 1 is very special.
Okay. And the second is whether you know of any result of continuity of the constants with respect to P and D.
No. Well, if you want, the physicist, there's a conjecture which says that if you let d and p to infinity, if you do d over p, which converges to some alpha, they have a sort of mean field model. And so the conjecture is that these constants should converge to the constants of the mean field model. But these are quite crazy, I would say, as conjectures. No, but, and I guess, no, there's also another case, which is if you fix, if you have alpha equals 0, so if you fix p equal 1 and you let d to infinity, there is some asymptotics for these constants, which are due to Lagrange. Yes.
Okay.
So this is, but this is the case where the physicists are interested in. For example, d equals p. D equals p, and you let d and p, which are equal to infinity. You should capture this kind of mean field models. But
Okay, thank you.
Thank you very much for your talk. It's just intuitively what happens in low dimensions? What breaks down for dimension 1 and 2 instead of...
Yes. So you have, the point is that you expect this number of points in a small cube. The heuristic says this, but you are forgetting about the central limit theorem. So if you have a random number of points, this is actually a binomial random variable of points. So you have oscillations which are of the order square root of n. And these oscillations give you some regions where you have much lower points, and then you need to import points from other regions around. So these oscillations in low dimensions compete with the actual number of points, while instead in larger dimensions they are negligible. This is why heuristics works and fails at large.
Okay. Don't see other questions, so thank you again, Dario.
Thanks, Giuseppe.
So it is a pleasure to introduce Alexander Milke from the Weierstrass Institute in Berlin. He will speak about on geodesic convexity and the EVI flow for the spherical Hellinger distance and the spherical Hellinger-Kantorovich distance. Thank you, Alex.
Thank you very much. Is the microphone working? Okay. So thank you very much to the organizers for giving me the opportunity to participate and to contribute to this beautiful workshop. Of course, there are many words in the title and I want to explain them. But before I do this, I want to mention that this is ongoing joint work. So some of the results are from 2 weeks ago and not everything is yet in the way that the technical details can be settled completely. But I also want to mention that this is joint work with, unfortunately, a group only of males, but the international diversity, Vaios Lassos is Greek, Matthias Liro is from Germany, Giuseppe Savare, you know, he's from Italy, Oliver C. from the Netherlands and Indonesia, and JJ Zhu from China. So, moreover, I want to mention that this ongoing work is ongoing for more than a decade, and it was crucially influenced by these workshops on optimal transportation and applications here in Pisa. I just want to mention that some of the papers here were really advanced or first discussed here in the workshop 2012 was my first OTA workshop, but I was in Pisa for other workshops before. So the point, of course, behind this Hellinger and Hellinger-Kantorowicz is unbalanced transportation. I have to learn to add the Asian at the transport because the title of this workshop is transportation. So what is unbalanced transport? Unbalanced transport means that you may transport, but you may also grow or decay. In the previous talk, you could disappear to the boundary and you could reappear at the other place. But if you come to Italy from Berlin, maybe you won't bring along your food from Berlin if you have to eat here because there's much better food here. So you leave the food in Berlin and you travel lightly, transport only the minimal costs in your suitcase, and if you come here, you go to the shop and buy good olive oil and other things. So that's the idea of transport and growth, and we all know that, of course, optimal transport is related to diffusion equations. So we have here in the classical way what I call the Otto gradient. So I don't want to use the W word because the W person did never write a gradient. So it's the Otto gradient of some functional E, but this describes diffusion. And if you buy or sell, then you can use the same differential. So this is the Gateau derivative of the functional, and this is the metric tensor which turns it into a tangential vector. And the same here, this multiplication transfers the dual vector into a velocity vector. This is the so-called Hellinger gradient. And altogether, the main point is that you have two linear operators here, and together we call this the Hellinger-Kantorowicz operator, which now depends on two parameters, alpha and beta. Alpha giving you the relative strength of diffusion, and beta the relative strength of growth and decay. So I explained this. The main point, of course, is that such an equation does no longer have mass conservation. So if you integrate the equation over the domain of, I didn't write it, of course, either it's the infinite domain or you have Neumann boundary condition. Typically, I work on finite domains to avoid probability measures with second moment, finite and things like that. So then you add Neumann boundary conditions, you integrate. This term does not change the total mass, but the last term here, this will can change the mass, and this mass term which comes up here, I will write it in this form. It's the duality between the potential and the measure. This will be crucial throughout the talk. So it will be on almost every slide because it changes the geometry at the end. So the point, of course, is if you have such an operator, K operator, I call these operators Onsager operators. These are differential operators, linear, acting on a potential and producing a derivative. You should think about this equation, which is the continuity equation, but now it's a continuity equation in the sense of Benamou-Brenier with an additional source term. So you do not only have the divergence, but you also have a source term here which can increase or decrease the total mass and the measure locally even. So this idea of Benamou-Brenier turning a metric tensor into a distance, this is written in this way. Here you have the differential operator. Usually you would write gradient v squared here, but this is, if k is including the divergence and the gradient, then you don't introduce the additional variable. But it's linear in mu here. You see it here, so you can write it in the sense of distributions. We can switch on alpha and beta. If we only use beta and put alpha equals 0, we arrive at the so-called Hellinger distance, and the Hellinger distance between two measures can be written by taking square roots and taking the L2 norm of the difference of the square roots. And if you only switch on the alpha and let beta equals 0, you get the 2 Wasserstein distance, and it's scaled by 1 over square root of alpha. So it's just to explain that the alpha gives you the strength of diffusion. If the diffusion is large, then the cost is low, of course, because you can move easily. The same with Hellinger. If you have a large beta in the equation, this means growing and decaying is very cheap. The main point is what we observed in our work with Giuseppe, that you can make all this rigorous, even though I write it here very colloquial, the continuity. If you want to look for the geodesics, you can just write what you expect from equations. You have the continuity equation and you have a Hamilton-Jacobi equation, but again the Hamilton-Jacobi equation has this traditional gradient square term, and now there's an additional source term. And from this equation, why is this equation is good? Because this operator has very favorable properties, and in fact that's why this operator was chosen, because it is not only a nice symmetric operator, positive semi-definite, defining the gradient, but it has two important properties. The K operator is a local partial differential operator, and second, it is affine in mu. So the mu shows up here and it shows up here. And this linear property is crucial for doing nice analysis. This linear property gives the fact that the Hamilton-Jacobi equation is not coupled to the measure. So you can solve the Hamilton-Jacobi equation independently. You don't, of course, to find the optimal geodesics, at the end they are coupled, but you can find the generalized Hoflachs formula for this equation, and this will be a crucial tool for studying the duality problem. So I want to address, really make clear that this is a very crucial property, that this Onsager operator is linear in mu. Not only that to make the analysis nice, but to have very good explicit formulations. Okay, but now we want to go to so-called spherical theories. And it's a little strange, the name sphere relates to the unit ball in L2, but the set of probability measures are spheres in a certain way. And that is because we think the probability space is a flat space. But if you know a little about transport theory, you realize, no, that's not totally true. Geodesics are curved, so it's not a flat space. And that's why this spherical is a little misleading, but I want to explain it. So now we want to go back from full measures. The Hellinger-Kantorowicz distance is defined on arbitrary measures because you can grow or decay, you can sell or buy, but you want to restrict now to probability measures. This means that you have to correct this equation if you want to have mass conservation in such a situation, so this is the equation if you write down a typical energy with an internal energy and a linear potential energy, you get this PDE. And now what do you have to do to have mass conservation? Well, you have to add an additional term here which corrects the mass source term. And of course, you don't want to do it arbitrarily. You want to do it in such a way that the resulting problem again is a gradient system such that you have a nice structure. And the only way of doing it is to add this term, which is the mass correction term here. However, you multiply it with u. You could also put a 1 here. It would still preserve mass, but it would destroy the gradient structure. And that's important. So this means this additional term, which I have written here explicitly, subtracts from the potential its mean value with respect to u. So this now has mean value 0 if you average over u, and that's why you have mass conservation. So this means we have introduced a new Onsager operator, a new gradient. This new gradient is the spherical Hellinger-Kantorowicz gradient, and it is defined by the Otto gradient plus a term which corrects the mass. And this new operator has two problems. It has the problem that it's non-local, and it has the problem that it's now quadratic in U. In fact, it's related to the problems which Gabriel explained in his talk when he said he wants to have mass conservation in his vector fields for these transformers. Then you get a non-local term, but you get additional non-linearity. And so the problem is, if this operator is no longer linear in U, you do no longer have a simple Hamilton-Jacobi equation which is decoupled, and you do no longer have a nice static formulation for calculating the distance squared. That's thing. So how can we find the spherical, oh, there's a typo, but I guess, can we do the Benamou-Brenier formulation? Of course, you can write down the Benamou-Brenier formulation for this new operator, just as before, and you get a minimization problem, and you can probably prove existence of minimizer. However, there is another, this will be very difficult, and there's another much better way which one can do. In fact, I learned this, of course, from Giuseppe, that there is a metric cone construction that you can consider the set of all measures as a cone over the set of probability measures, because every measure can be written as a multiple of a probability measure. And now the point is, the right scaling is not mass times probability measure, but the right scaling is R squared times a probability measure. And this square makes the probability set into a sphere, because you take a square root. So you take R to be the square root of the mass. And if you do this, this is very traditional, classical construction in geometry. You can find it in this Burago-Ivanov book. And the point is, why is this the right thing? The right thing is you can check that the Hellinger-Kantorowicz distance, if you put this scaling in front of measures, has a nice scaling property. And the scaling property is if you put a factor R0 squared to the first measure and R1 squared to the second measure, the result you get is the product of the two measures times, there should be nothing in here, sorry, that's a typo. The Hellinger-Kantorowicz distance without any scale plus a correction, and this correction only depends on the total mass. This you can just, if you have the static formulation, or you can put it in the Benamou-Brenier formulation, you can prove that this is, it's not too difficult to prove that, if you know what you are looking for. And this is exactly the condition in this book. If you have such a distance which has this property, then you can prove that the induced distance, if you go from the full cone to the base space, that the induced distance is given by such a formulation. We all know if we have a distance from, let's say, Pisa to San Francisco, there is a straight distance where you drill through the earth, and there's the distance walking along the sphere, and this is longer, of course, to go along here. Walking along here is the induced distance, induced from the Euclidean space, while going straight is the Euclidean distance. And you have this formula. These corrections here are just because I have included this beta, so that's not important here. So you have an arc-sine relation. But what you will learn is that the spherical Hellinger-Kantorowicz distance is not a power of a local integral. Like in Wasserstein P distance, it's an integral over something. So you have additivity in a certain way. But here, to have this is the square root of an integral representation, so you have to take a sine function. So this makes life a little more difficult, and it explains that non-locality leads to new effects. This is the non-locality. Okay, so in fact you can even write down the geodesic constant speed geodesics in the spherical Hellinger-Kantorowicz formulation. But if you know the geodesics in the Hellinger-Kantorowicz situation, and you have exact formulas which you can find in the Burago book, and everything is well done. But of course the point is that the probability measure with this Hellinger-Kantorowicz distance would not be geodesic, and the spherical one is the induced length distance, which is geodesical. And again, we think about the probability measures like this, but in fact, because there's mass lost when you connect the distance, it's like going through the earth. If you want to go to San Francisco, that's why you have to do this correction. And this mass loss was already observed in older papers almost 10 years ago. That there is an explicit formula for the mass along Hellinger-Kantorowicz distance, which is just a quadratic function. And this relates to the cone construction. Okay, so now let's do some differential equations. I want to do evolution. So the guiding question is, what can we learn, like geodesic convexity or existence of EVI flows, if we from the Hellinger-Kantorowicz information for the spherical case. So if we already have studied the Hellinger-Kantorowicz problem, can we learn something for the spherical Hellinger-Kantorowicz? And as a warming up example, I want to look only at the Hellinger case. Just forget about transport, because it's getting involved. Even already here, it's getting involved a little. And I look at the most simple problem you can think of. Take these measures, take the Hellinger distance, and the functional you look at is the distance squared with respect to some point. all who have studied a little metric evolution know what are the solutions. If you start at some point, you follow the geodesics with speed e to the something times minus something times the time. So you follow geodesics which connect from the initial point to the final point. But so the geodesics in the Hellinger distance are explicitly given. You take the square root of the measures and you interpolate and then you square. So they are exact formulas and you can write them in this way. So there is a linear interpolation between the measures and you subtract something. And this something depends on the square root of two measures. And I want to mention this here. This square root is sometimes called Hellinger integral or Hellinger-Kakutani square root. And it was introduced in 1907 in the habilitation thesis of Christian Hellinger in Göttingen. And the name was attached to it by Kakutani in 48. And Kakutani already knew about Radu-Nikodym derivatives, and that's how you define it in Radu-Nikodym derivative. However, Hellinger did it 20 years before Radu-Nikodym theory existed, and he used a formula like this. This is the Kolmogorov way of doing it. So you can define it without Radu-Nikodym derivative. You partition, and on each small interval you take the square root, and now if you partition further, the square root is concave, then it's going down. So the finer you partition, the lower the integral is. So you can do it. So this is a disjoint union here. And I just want to explain that Hellinger is the right word for this distance and not what other people use. I will come to this later. So the observation is that this Hellinger distance is surprisingly special. It is like a Hilbert norm. It is too convex and too concave, like in the Hilbert setting, because essentially what you are doing here is you transform it by a square root to a L2 space. And you can prove that you have a contraction semiflow. Everything is simple. You can write down the equation. The equation looks a little nonlinear. If you write the equation like this is the Hellinger gradient here. And it looks like this, that you have beta is just the prefactor, square root of u minus u. So u equals 1 corresponds to the steady state, because now u is the relative density with respect to the base measure. But you observe, of course, that this equation has a lot of steady states. U can either be 0 or 1. Any function which takes only values 0 and 1 is a steady state because the right-hand side vanishes. This contradicts the idea of having a contractive semiflow if you have infinitely many steady states. So I want to make this point here that we expect contraction because we have a nice convexity property, and we can write down solutions. However, this solution you can write U0 is the initial condition, is an explicit solution, and this really satisfies this property here. However, there are other solutions. If you start at 0, you can stay at 0, take a random clock, and go for lunch later than the others. So you can shift your departure from 0. So there are infinitely many solutions. And the solution, of course, is here that these solutions which stay 0 for some time are not curves of maximal slope. You can calculate that. It's a nice example for the students to learn the theory. So you can prove if the solution stays 0 on a certain set B, then outside of a certain set B, then the metric slope is smaller than the metric velocity is smaller than the slope, and so it cannot be a solution. The point is you have an EVI flow for this problem, and the EVI solution is a solution which immediately leaves zero. In the metric gradient flow theory, this is the only admissible solution. So that's a good case that the gradient theory selects a type of solution which is unique, while people who look at the PDE will not see the uniqueness. So now let's go do our program. Now we want to go back to the probability measures and use the spherical Hellinger distance. If you reduce the Hellinger distance to some submanifold, then this is called the Fischer-Rao distance of this submanifold. This concept was introduced by Rao in his fundamental paper in 47. Take the Hellinger infinitesimal metric, which was written down as Fischer's by Fischer already in 21 for finite dimensional submanifolds. Take the logarithmic derivative of the density and integrate it with respect to the density itself. Then this induces a distance on the submanifold, and this is called the induced distance is the Fischer-Rao distance of the submanifold. So I do not agree that Hellinger equals Fischer-Rao. Some people do it, but it's not good to call Hellinger Fischer-Rao, because then you cannot make this statement here that the Fischer-Rao distance is bigger than the Hellinger distance. So of course you just have to know that weak convergence for stochastics people is different than weak convergence for functional analysis people, because the stochastic people mean weak star convergence. So if you read French papers, please don't put an equality here. So the spherical Hellinger distance is the Fischer-Rao distance for the probability measures. And it's given by this formula, and the arc sign is certainly above the straight line, so it's bigger. Now, what is the equation you are looking at now? Now, of course, we restrict to probability densities. The equation now is the equation as before, plus this correction term, which corrects the mass density. And I have abbreviated this QU here, just to make the following formulas. This is the mass correction term. And in this special case, of which I have chosen, if you calculate this term, you see that the square root of u, this gives u minus square root of u, and you can do a little calculation, and you see it's exactly the Hellinger distance from 1, with a factor 1/2. This is not an accident, it will come out later, even in other cases. So now what we want to do is we want to understand contraction properties. We want to understand contraction properties, and we know already that all solutions have to leave zero immediately, otherwise they are not curves of maximal slope. So you can do the calculation by assuming that u and v are positive. Then you just do it and you calculate a little and you find out, you get a very simple identity. The right-hand side, this derivative is just given by a factor Hellinger squared. And the prefactor here is this 1 coming from the Hellinger flow, and these 2 green terms coming from the mass correction term from the spherical case. But they are also multiplied by the same factor, because this mass correction term now looks like this. And if you integrate out, you see again this is the same as the Hellinger distance. So at the end you see that this favorable 1, which is the contraction rate of Hellinger, is deteriorated by these 2 terms. I still have a because of this QU and QV being 1/2 of the Hellinger distance, and the Hellinger distance is bounded by 2, these two terms are still together not bigger than the term 1. So you still have a contraction estimate. So you still have a contraction estimate. So you have existence and uniqueness of solutions. Well, you get uniqueness from here, and existence you can prove by hand here, of course. But what you learn is the nice contraction in Hellinger is destroyed by this mass correction term. However, that's the main message of my talk. Look at sublevels. If a solution starts in a sublevel, it will stay in the sublevel. So now I define script S of E is the sublevel where the energy is less than E. Now these QU terms are exactly given by the energy. So if I take this equation and I use the fact that this term is less than 1/2 E, then it's not a 0 which I get here, but then this term will be 1 minus E over 2. Because each of the QU and QV will be less than E over 2. So this means if I take two initial conditions in a sublevel with energy E, which is strictly less than 2, 2 is the maximum of the energy anyway, then I will still get a positive bound here. And this positive bound gives me now a contraction rate, and it tells me that the energy is geodesically lambda E convex if I restrict the energy to a sublevel. So the suggestion or the outcome of this discussion which we had in May in Milano is that one should look at something like sublevel EVI solutions. And sublevel EVI solution says you have a curve and which has, of course, a bounded energy. It's called a sublevel solution if it satisfies an EVI solution, if it satisfies an EVI. However, the lambda in the EVI may depend on the sublevel in which I take the comparison W. I cannot guarantee that everything is nice very far outside. So if the further I go out, the more careful I have to be. That's the idea. Of course, if I know that I have two solutions, I know the energy decays, and then I can compare these two solutions in one of the sublevels. So that's the idea, and now let's try to do the same for going from Hellinger-Kantorowicz to spherical Hellinger-Kantorowicz. Of course, lambda convexity in Hellinger-Kantorowicz is a quite difficult thing, and the good thing is in this talk I say, oh, this was solved, but somehow I only do this next step, and I don't want to think about Hellinger-Kantorowicz. I want to devise a method which is not using how you get the lambda convexity for Hellinger-Kantorowicz. I only want to know how do I go the next step. So, and here the idea is to use the autocalculus, which was introduced in the paper by Otto in 2000 and continued by Giuseppe and Sara Daneri later on. So imagine you have a geodesic distance which is generated from a K operator, so from some pseudo-Riemannian structure by the Benhamou-Brenier argument. Then you ask, when do you have geodesic lambda convexity? Geodesic lambda convexity is defined like this. If you walk along a constant speed geodesic, you can estimate the function from above by the linear interpolant and this parabolic correction. This is the definition, but there are equivalent formulations. And the equivalent one of the equivalent formulation is you calculate the Hessian. The Hessian is sort of like the second derivative, but now on a Riemannian manifold. And this Hessian has to be bounded from below by lambda times the metric tensor, or the Onsager operator in my case, because I'm working on the dual space. It's the inverse of the Riemann tensor. Or equivalently, it says that you have a semigroup, and this semigroup has a lambda construction, is a lambda contraction. So that's the idea. Of course, this is in some sense formal, because what is the Hessian? The Hessian here is, of course, a complicated fourth order differential operator. So it's applying the Otto operator to the second derivative of the E, and then again applying the Otto operator. So it's here, it's written in a way, and then there are corrections which come from the fact that the metric tensor is changing. These are like the Christoffel symbols you know from classical differential geometry. These terms. So this is a way of writing it. And now the point is this of any use? Here are the conditions. The time is running, which we derived and published last year finally, that for internal energies you can write down explicit sufficient and necessary conditions which generalize the Mecan conditions in the geodesic convexity in the Wasserstein 2 case, and also the Hellinger convexity. But I will skip over this and just return to my question of the passage from HK to SHK. So the main point is, as I explained earlier, the spherical Hellinger-Kantorowicz gradient is defined with this operator. And this is simply given by the HK operator plus this correction term, which now is quadratic in U. Or you can say it is applying the Hellinger-Kantorowicz operator to the potential psi minus its average, so it's applying it to functions with zero average. But observe that this projection is itself depending on U. However, I can still use this nice property that HK operator is linear in U, and the other point which is behind of this construction is that if I apply the constant 1, this is a constant function in space, to the Hellinger-Kantorowicz operator, I get beta times U, because the Hellinger term just gives this. So these are the important properties. If you have these two properties, one can prove the following theorem. So you see it's November, last week of November. I redid this calculation several times. Sometimes I took 3 pages, and now I hope I have a proof of it, which is less than 1 page. The Hessian in the spherical geometry can be expressed by the Hessian in the flat, not in the flat case, but in the full measure case, in the HK case, by just applying it to the projected potentials plus, or better, minus a correction term, which is the mass production term times the geometry of the spherical situation itself. So this is a quadratic form and this is a quadratic form. This is a local differential operator, this blue stuff. But here you have non-local terms, here you have non-local terms. Here you have a product, this is an integral, a local operator. And this is another integral, again, so it's a product of two terms. So you see you have completely understood where non-locality comes into play. It's on a very controlled level. And the good thing is that this was done last year. The Hellinger-Kantorowicz case is understood. If we have estimates here, we can apply a corollary. We can define sub-level geodesic convexity. If you restrict to a sub-level, you can give a lower bound on this quadratic form by the lower bound from here, because this can be bounded from below by the operator from HK applied to the normalized projected potentials, but that's exactly this one. And then this term has to be estimated by taking the worst case in the sub-level. That's exactly what we did in the Hellinger case. So the formula is exactly the same as in the Hellinger case. Nothing has changed, and that's a big surprise. And now you can use this for PDEs. For these PDEs, of course, there is a lot of work. They were studied mainly in the French school, but there are some, at that time he was, Mont-Saint-Jean was in Portugal and working. Florentin Fleissner in Munich has done some work. So here is a case where all the theory applies. You take a energy like this, which has minus a square root here. Minus square root is Hellinger-Kantorowicz convex in 1 and 2 space dimension, not in 3 and higher, but in 1 and 2, so it still works. So this gives you this PDE, and because of the square root here and the square root here, you have non-uniqueness of solutions, and as before, curves of maximal slope have to leave 0 immediately, and this weak solution concept gives you too many solutions. So I don't want to go into detail here, but now the main question is, can we define sub-level EVIs? So we have the sub-levels as before, and now we want to define for a given threshold E, we want to define the maximal problem we can get from the mass correction term. So we take the supremum over this mass correction. There's a D missing here, sorry. And so let's look at standard entropies, whether it is possible to control this term by the energy. And the surprise is, yes, it's very simple. If you take the Boltzmann entropy, U log U minus U plus 1 plus a linear term, if you calculate the derivative, you get, from here you get a log U, you multiply it by U, so it's the same. These two terms don't matter on probability measures because they integrate to the same constant 1. So in fact, for the relative Boltzmann entropy, you get QE equals E. So it's very simple to estimate the influence of this term by the energy. If you have a P divergent, the problem is that this doesn't work with Hellinger-Kantorowicz, but that's a different thing. If you can take any P divergence, and you will find out that a similar thing happens, you just get a factor P here. So this mass correction term is just a constant times the energy. So you have Q of E is PE, so it's easily controlled. Then with Vios-Lachos, we worked on the case where E prime is negative. E prime being negative, integrated against the positive density, always gives something non-negative, non-positive. So you have QE is bounded from above by 0. So this bad term can be controlled in some cases. It cannot be controlled if you have E2 U, but I don't know anyone who has studied such a case. So polynomial growth is okay. Now you can do EVI constructions. How do we do that? Well, we study the Muratori-Savare trilogy. Only the first volume is out. We are still waiting for the second volume, but I was lucky that in 2012 I got a preprint which has 40 pages and it contains the main things. And so Vajos and we studied this heavily. And from that you can find out that if you have lambda convexity and some other problems, the minimizing movement schemes provide solutions to EVI. And the two technical conditions you need is the so-called local angle condition, which is sort of, for Riemannian situations, this is trivial. And for all the applications we have in mind, it's also trivial. However, there's another important quantity, which is the kappa concavity of the distance. So the distance should not be lambda convex, but it should be chi concave. So there is a k here, and this is the opposite sign. It relates to positively curved spaces. If k equals 2, so big K is bad, of course. Like negative lambda is bad for convexity, but having some lambda is, of course, good. So in Hilbert spaces, you have local angle condition, 2 concavity and 2 convexity, and the same is true for Hellinger. Hellinger is like a Hilbert space, so it's the best you can think of. If you take the spherical Hellinger, then I did some rough calculation. You still have concavity, but with a factor much bigger than 2. It's not yet optimal. I will optimize it. And I also proved convexity with a negative value. I believe it's true with a positive value, but it's not important here. For Wasserstein 2, it is known that you have 2 concavity if the underlying space is 2 concave. But the flat space is a Hilbert. So in my case, I take always a convex subset of RD, which is a flat space. You can find this in the green or the book. And for HK, the result is strange. In 1 dimension, it's true, and in low dimension is different. Dimension 1 is especially different. And in 2 dimensions, it is wrong, and higher, it is wrong. So the HK distance is not kappa concave. And then if you do spherical, you should not expect to make it kappa concave. So that's the problem, why it took quite some while and the smart arguments of Vajos Lashos to make the theory work. So the theory can be made work if you restrict to densities which have a lower bound positive and an upper bound positive. Then you can prove that the transport plans again have lower and upper bounds, maybe not the same, but still bounded away from 0 and bounded away. So the geodesic curves, I mean. So you keep the 2 endpoints in this set, then you have some kappa concavity, K concavity. I say kappa because it's a Greek capital kappa. So it's like a lambda. So the result now is the following. If you have either the Hellinger-Kantorowicz situation or the spherical Hellinger-Kantorowicz, you know that the Hessians are bounded from below on sublevels. So we know how to prove this here if we know it here. Moreover, we should know that if you take the geodesic hull of a sublevel, that you stay in another sublevel. Because you have to compare between 2 points, but the sublevels are no longer geodesically convex, but you stay in a bigger space. Then you also should we restrict to this special case, so nonlinear diffusion equations with a smooth potential, then the minimizing movement scheme generates an EVI flow on sublevels, an sublevel EVI flow, and the constant on the sublevel SE is not the lambda E, but it's the lambda HE because you have to go to the bigger space. And that's, and of course, if you have this, then you have a contraction estimate on the sublevels. It's not, this lambda is negative, of course, usually, so, but still you have Lipschitz continuity. The proof is just to slightly adapt the Muratori-Savary results. And the first only thing is to prove that these upper and lower bounds on the densities are preserved in the MMS scheme, and there we use the preprint Otto, which is sort of the preprint for the JKO paper, which has some surprising good estimates which didn't end up in the SIAM published version. But you have to generalize it from the optimal transport to the logarithmic optimal entropic transport problem, but this works similarly. And you can, if you know that you have initially upper and lower bounds and you have a fixed time interval, you can prove that the bounds are uniform with a time step and everything. And then you have this important estimate here. You see there is no unknown constant here. This is Giuseppe's work. So if he does it, there is no unknown constant. There's a 2 and a 4, and that's it. So you can compare two geodesic interpolators of the minimizing movement schemes, and it's square root of the maximum step size, which you have here. If you initially have slope, it's in the Green Book in chapter 3, there is a result of this type, but there the special Wasserstein situation is used. These, how is it called, generalized geodesics, which are not available. And this, to replace this by kappa concavity, this is the masterpiece in this volume 3 of the trilogy. And then you pass to the limits, everything is uniform, and it's time for lunch. So I just want to conclude to remind you that going from Hellinger-Kantorowicz to spherical Hellinger-Kantorowicz, you introduce a new, and I think it's a geometric correction term, and I would really love to hear that someone says, yes, this term is known, it exists in this and that theory, because it seems to be very intrinsic, and using this you can conclude. And I want to thank you for your attention, for staying to the end of this beautiful conference. And maybe before you applaud me, we should applaud the organizers. The number of organizers has slightly decreased, but nevertheless, we all agree that this is not something which is we all agree that this was a beautiful conference and we learned a lot, and we hope that optimal transport is carrying on, transported also into the 2 years later, and that the organizers will make sure that we stick together and learn more from each other. And thank you very much to all 5 of them for having us here and making this just a great success.
Thank you, Alex. I didn't pay you for all this publicity and also the final thanks. And are there questions?
So do you have cases where such gradient flows are then correspond to some, say, models coming from physics or biology, or which would be the range of energies for which you can actually prove existence of the flow? What does it correspond to?
At the moment, we do not have a striking application. So with JJ Zhu, we are working on applications in data science and modeling of minimization problems. There, the algorithms of this type are used because if you have data clouds and you want to compare them and move them, sometimes it is good to reweight and say, oh, these data points are not so important, let's reweight them. But at the end, you want that the total sum of data points has the same constant weight as before, because otherwise everything might converge to zero. And so in that respect, equations of this type are used for such modelings, but for partial differential equations, I have to admit, I do not know the right model which is sort of there. I didn't check. Didn't mention this paper by Carrillo, Huang, and Wei. I should. It was written somewhere, but here on the top, this is a paper from July. They may have something, but I do not.
Are there other questions? If not, let's thank Alex again. I will also add some particular remarks and thanks for the staff of Scuola Normale and Centro De Giorgi that helped us a lot for the organization of the conference. I would also like to thank you all. I think that today we have the record for Friday morning in the past 10 editions. So thank you very much for staying with us till the end of the workshop. And I also join Alex to hope that we will reconvene in 2 years here. So thank you again for everything.